Now let's see what inverse, sine, cosine, and tangent functions are. So basically, I think you've seen this before. The sine inverse function is defined like this. If y is equal to sine inverse of x, then x is equal to sine of y, right? Basically, if this sine is taken to the left-hand side or any opposite side of the equation sign, it becomes the sine inverse function, right? But there's a limitation to this. See, x can only have a value of -1 and 1 and anything in between, right? So it lies between -1 and 1, as you can see in the graph of a sine function. This is 1 and this is -1. It will always lie, the value will always lie between these two values. So when you plug in these values of x and then sine inverse that value, it will always lie between -π/2 and π/2. Okay? Now, similarly, for an inverse cosine function, you have the same equations except in terms of the cosine, and x again will always lie between -1 and 1, as the graph is same but the phase is different for a cosine function, right? It's something like this, right? But again, it's between 1 and again -1. So if you plug in those values of x that are between 1 and -1, the value of y that we'll get from the inverse cosine of x will always lie between 0 and pi. Okay, so the inverse tangent function, again, the value of x will lie between -infinity and positive infinity, right? As you can see, the graph of tangent is something like this, right? But again, if you make a line over here, the value of x will keep on going till infinity and again till -infinity. So which is why the value of x can have any value. But if you plug in any value of x over here and take the tangent inverse, the value of y that results will always be between -π/2 and π/2. Now again, you apply the same logic for the cotangent, secant, and cosecant functions, right? Again, the x value of a cotangent function can be any value between positive infinity and -infinity. But again, if you plug in those values over here and take the inverse cotangent, you'll get a value between 0 and pi. And again, for the secant function, the value of x will always be greater than 1, right? So if you take any value of x, the modulus of x, the absolute value of x will always be greater than 1. So right, so x cannot have a value between -1 and 1, right? So again, it will always be greater than 1 and less than -1, which is why when you plug in those values, you'll get a value of y. If you plug in those values over here and take the secant inverse, you'll have a value between 0 and pi, except that you will not have a value of y that is equal to pi/2, because I think those values lie in this region, right? Okay, so again, the inverse cosecant function is like this, and again, it's the same for x. The absolute value of x must be greater than 1, so it will always be less than -1 and always be greater than 1, nothing in between. So when you plug in those values over here and take the inverse cosecant function of those values, you'll get a value of y that is between -π/2 and pi/2, but not including 0. Okay, so yeah. Now, let's show that the tangent inverse function, whoops, sorry, seems to be an issue, yeah. Let's show that the tangent inverse function is equal to the sine inverse function if given the right circumstances. Now, we have to show that the tangent inverse of 5 by 12 is equal to the sine inverse of 5 by 13. Now let's see how. Basically, sine inverse 5 by 13, let's give it a value equal to a constant called alpha, right? So when you take this sine inverse function to the right hand side of the equal to sign, you get sine of alpha, right? Because that's just the rule. So sine of alpha is equal to this value, 5 by 13, right? So now we know that tangent alpha is equal to sine of alpha over cos of alpha, right? Cosine of alpha. So we can replace this cosine of alpha with under root 1 minus sine square alpha. How you say? Well, you remember this trigonometric identity, that sine square of x plus cos square of x is equal to 1, right? So when you take this sine square of x to the right hand side, it becomes minus sine square x, so 1 minus sine square x on the right hand side, and then you take the under root on the right hand side to get cosine of x, right? Which is why cosine of alpha is equal to under root 1 minus sine square alpha. Now replace the sine alpha values in this expression, right? So we already know that sine of alpha is equal to 5 by 13. So this in the numerator becomes 5 by 13, and this sine square alpha becomes 5 by 13 whole square. So now do all the calculations, and you eventually end up with 5 by 12. So tangent of alpha, right, is equal to 5 by 12. Now you can take this tangent function to the right hand side, where it becomes tangent inverse. So alpha is equal to tangent inverse 5 by 12. And so we already knew that alpha was equal to sine inverse 5 by 13, and now we've proven that alpha is also equal to tangent inverse of 5 by 12. So you've proven the equation. Now let's see how you can find the value of this expression. Okay, now it says we have to find the value of cosine of sine inverse 1 by under root 2, right? So first let's deal with this bracket as we do in maths. So let's give this sine inverse 1 by under root 2 equal to y, right? An arbitrary value. So when you take this sine inverse function to the left hand side of the equation, it becomes sine, right? So sine of y is equal to 1 by under root 2. Now in this case, we already know, as we've discussed before, that the value of y lies between minus pi by 2 and pi by 2, right? So if we see that the value of sine y is equal to 1 by under root 2, you can use your previous knowledge to find that the value of y will be equal to 45 degrees, right? Because sine of 45 degrees is 1 by under root 2, and 45 degrees in radians is pi by 4. So that's why we have this pi by 4 here. So y is equal to pi by 4. Now, since we already know that y, which is equal to sine inverse of 1 by under root 2, is equal to pi by 4, all you have to do now is replace that in the original expression, right? Replace that over here. So you replace pi by 4 in this expression to get cosine of pi by 4. And that, as we already know before, is 1 by under root 2. Now let's see the addition and subtraction formulas of the inverse trigonometric functions. So let's look at this one here and let's prove it, and the others will become very easy to understand once you understand this one. So it said that sine inverse of a plus sine inverse of b is equal to sine inverse of a into under root of 1 minus b square plus b into under root of 1 minus a square. So how did we get here? Well, see this, basically if you say that x, let me not write it here, let's say that x is equal to sine inverse of a, right? So this is x. Let's say sine inverse of b is y, right? So y is equal to sine inverse of b. So clearly, if you take the sine inverse to the left-hand side of the equations, it becomes a is equal to sine of x and b is equal to sine of y. So a is equal to sine of x, b is equal to sine of y. Now, let's see what we can get for the cosine. We already know the trigonometric identity, that sine square of g plus cosine square of g is equal to 1, right? So if you apply the same trigonometric formula and convert it for the cosine, it becomes cosine of g. Let me just drop this off. Just a second. Yeah. So cosine of g from this becomes equal to under root of 1 minus sine square of g. Now apply this one to both of these equations. So that means that cosine of x, wait a second, so cosine of x is equal to under root of 1 minus sine square of x, and similarly cosine of y is equal to under root of 1 minus sine square of y, right? Now let's look at another trigonometric identity which says that sine of x plus y is equal to sine x cos y plus let me just sine y cosine of x, right? Now apply that. We already have the values of sine x, sine y, cosine x, and cosine y, right? So apply those over here. So sine of x plus y is equal to all of these, and yeah, sine of x plus y is equal to sine of x, which is a, into cosine of y, which is basically 1 minus sine square of y, and basically that becomes equal to, let me just write that down, sine of x cosine of y under root 1 minus sine square of y. Now what was sine y? Sine y was equal to b. So what is sine of sine square y? It is b square, right? So b square plus sine y cosine x. Sine y was equal to b, right? Into under root of whatever cosine of x is what cosine of x. Cosine of x was equal to 1 into under root. So it was equal to under root of 1 minus sine square x, and sine square x is a. So under root 1 minus a square. Under root 1 minus a square, right? So x plus y would become equal to take the sine inverse function to the right hand side. Sine inverse of a into under root 1 minus b square plus b into under root of 1 minus a square. And so we already know that x was sine inverse of a and y was sine inverse of b. So this is how you prove this first addition formula. And similarly, all of these that you see here can be proven by similar trigonometric identities, right? This one as well, using the tangent trigonometric identities, and this one as well. But yeah, all of them can be proven when you first equate these terms to arbitrary constants and then apply the trigonometric identities. Now let's prove that the sum of two sine inverse functions is equal to a cosine inverse function. So we have to prove that sine inverse of 15 by 13 plus sine inverse of 7 by 25 is equal to cosine inverse of 253 by 325. So how do we do it? Well, first thing you do is take this cosine inverse function to the left-hand side of the equation. So cosine of sine inverse 15 by 13 plus sine inverse 7 by 25 is equal to this number, 253 by 325. Okay, now let's give sine inverse of 15 by 13 and sine inverse of 7 by 25 arbitrary values, namely alpha and beta, right? So sine inverse of 15 by 13 is equal to alpha, and sine inverse of 7 by 25 is beta. So this equation becomes cosine of alpha plus beta, right, is equal to 253 by 325. Now, replace cosine of alpha plus beta with its trigonometric identity value, right? So cosine of alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. Now, sine alpha was given to you as 5 by 13, and sine beta was given to you by 7 by 25, right? Because as we said, alpha was equal to sine inverse of 5 by 13, and beta was equal to sine inverse of 7 by 25. So once you take the inverse functions to the other side of the equation, you get these. Now, cosine alpha is equal to under root of 1 minus sine square alpha by the trigonometric identity again. And when you apply the same trigonometric identity on beta, you get this. So cosine alpha is equal to 1 minus the square of sine alpha. Sine alpha is 5 by 13, so 1 minus the square of 5 by 13, which is this. Similarly, since sine beta is 7 by 25, sine square beta will be the square of 7 by 25, which is 49 by 625, right? So cosine alpha is equal to under root of 144 by 169, and cosine beta is equal to 576 by under root of 576 by 625. So you get these values respectively, and now replace them in the cosine alpha plus beta, right? So cosine alpha plus beta was equal to cosine alpha, which is equal to 12 by 13, into cosine beta, which is now equal to 24 by 25, minus sine alpha and sine beta, right? Sine alpha and sine beta. So the value turns out to be equal to 253 by 325 exactly. And alpha plus beta, when you take the cosine to the right hand side of the equation, gives you equal to alpha plus beta is equal to cosine inverse of 253 by 325. So now you've proven this equation. Now let's see how you can solve the tangent inverse function. So it says we have to prove that the tangent inverse of 1 by 4 plus the tangent inverse of 1 by 5 is equal to the tangent inverse of 9 by 19. Let's prove this. So let's suppose that tangent inverse of 1 by 4 is equal to x, right? So tangent of x is equal to 1 by 4. Now again, similarly for tangent inverse 1 by 5, let's suppose that's equal to y. So tangent of y is equal to 1 by 5. Now, we know this trigonometric identity that tangent of x plus y is equal to tangent of x plus tangent of y over 1 minus tangent x tangent y, right? So we already know that tangent of x is equal to 1 by 4 and tangent of y is equal to 1 by 5. Now, plug those values in to this equation. So tangent of x plus y is equal to 1 by 4 plus 1 by 5 over 1 minus 1 by 4 into 1 by 5. So this turns out to be equal to 9 by 19. So x plus y is equal to tangent inverse of 9 by 19, right? Because tangent of x plus y was equal to 9 by 19, so x plus y is equal to tangent inverse of 9 by 19. So tangent inverse of 1 by 4 plus tangent inverse of 1 by 5 is equal to tangent inverse of 9 by 19. A very simple proof that we have done. Now let's prove that the tangent inverse function is equal to the sine inverse function in a certain case. Let's prove that 2 tangent inverse of 2 by 3 is equal to sine inverse of 12 by 13. So tangent inverse of 2 by 3, let's denote it by x. So that's equal to x. Now take the tangent inverse function to the other side, which means that tangent of x is equal to 2 by 3. Now, we know this trigonometric identity that sine of 2x is equal to 2 tangent of x over 1 plus tangent square of x. So we already know that tangent x is equal to 2 by 3. So just replace that value over here. So this tangent x becomes 2 by 3 and this tangent square of x becomes 2 by 3 whole square. So now this turns out to be equal to 12 by 13. So sine 2x is equal to 12 by 13, which means that 2x is equal to sine inverse of 12 by 13. And so you clearly see that 2 tangent inverse of 2 by 3 is equal to sine inverse of 12 by 13, because this x is equal to tangent inverse of 2 by 3. So 2x is clearly equal to 2 tangent inverse of 2 by 3. And so you've proven the equation. Now let's prove by using the sine double angle formula. So we need to show that the sine of 2 cos inverse x is equal to 2x into under root 1 minus x square. Seems a bit complicated, but it's pretty simple. So let's denote this cosine inverse of x as alpha. So clearly x is equal to cosine of alpha, and alpha will obviously lie between 0 and pi, right? Because that's the rule of the cosine inverse and the cosine functions. So sine of 2 alpha is equal to 2 sine alpha cosine alpha, right? That's the sine double angle formula. And again, this is also equal to 2 cosine alpha into under root sine square alpha, right? Both of these apply for the sine 2 alpha. And again, the third one is 2 cosine alpha into under root 1 minus cosine square alpha, when you replace the sine square alpha with 1 minus cosine square alpha by another trigonometric identity. So clearly we denoted cosine alpha with x, right? So you replace this cosine alpha with x and this cosine square alpha with x square, right? And now sine of 2 alpha is equal to sine of 2 into cosine inverse of x, right? Because cosine inverse of x was equal to alpha. So this alpha becomes cosine inverse of x, and you get this. And that is exactly what the question asked of us. Now let's solve the tangent inverse function. Very simple. We need to prove that the tangent inverse function is an odd function, meaning that tangent inverse of minus x is equal to minus tangent inverse of x. So the first thing you do is you take this minus tangent inverse of x to the left hand side, not just the tangent inverse function, the entire thing. So now we need to prove this. So let's see how the left hand side becomes equal to 0. Well, you take the addition formula, right? You take the addition formula of the tangent inverse function, and that gives you this. So tangent inverse of minus x plus tangent inverse of x is equal to tangent inverse of minus x plus x over 1 minus negative x into negative x into x, right? So this numerator becomes 0 because it's minus x plus x, and the denominator becomes 1 plus x square, right? And since the numerator is 0, the entire bracket becomes 0. And tangent inverse of 0 is, well, 0. So now we've proven this equation, and just take this tangent inverse of x to the right hand side, and you've proven the original equation given in the question. Now let's solve the tangent of a sine inverse function. So let's show that tangent of sine inverse x is equal to x over 1 minus x, 1x over under root 1 minus x squared, right? Let's prove this. So as always, replace sine inverse x with an arbitrary constant, let's say alpha. So sine inverse x is equal to alpha, so obviously sine of alpha is equal to x. And since this is a sine function, alpha will always remain between minus pi by 2 and pi by 2. This limitation comes from the inverse, right? So yeah, tangent of alpha is equal to sine of alpha over cos of alpha. Now when you apply the trigonometric identity that sine square alpha plus cos square alpha is equal to 1, the denominator can be replaced with under root 1 minus sine square alpha, right? When you take the sine square of alpha to the right hand side, it becomes 1 minus sine square alpha. So cos square alpha is equal to 1 minus sine square alpha. So obviously cos of alpha will be equal to under root of 1 minus sine square alpha, which is why you have this in the denominator now. So now what you'll do is you'll basically replace the sine alpha terms with x, right? Because that's what we did initially. We said that sine inverse of x is equal to alpha, so sine of alpha is equal to x. So since sine of alpha is equal to x, this sine of alpha in the numerator becomes x, and this sine square alpha becomes x square, right? And now you've since tan of alpha is equal to x over under root 1 minus x squared, tan of sine inverse of x is also equal to x over under root 1 minus x squared, because alpha, as we said initially, was equal to sine inverse of x. So now you've proven the original equation.